Welcome to InsectTech's Ethical Hacking course videos. Module Buffer Overflow and Exploit Writing. In this video, we will go through the basics of buffer overflows and exploit writing. We will start from the very basics and we will try to understand what are the exploits types and what are the attack methodologies and what are the steps involved in writing an exploit, and finally we'll try to exploit a simple buffer overflow vulnerability by writing our own exploit. So to start with, what is a buffer overflow vulnerability? So before understanding buffer overflow vulnerability, let us try to understand what is a buffer. Buffer is a small memory area which holds some data. So when we accept some data into this buffer which is out of a limit, it overflows, and this is called buffer overflow. So buffer overflow is a situation arises when you try to put the data in an array which is more than the size of the array, and we haven't put any exception handling. So we keep on filling the array, but the time comes when array ends, you overwrite that what was there, and we will see what it is exactly using a live example. And exploit is a piece of software that takes advantage of a bug in an application or a software. Let us say we have a buffer overflow vulnerability. Now we'll write a simple exploit to take the advantage of that buffer overflow vulnerability, and this is a simple piece of code, and this is called exploit. And this exploit consists of two things. One is payload and another one is code to inject the payload into the vulnerable application. Now to start with the very basics, let us first try to understand what is a byte and what is a word and what is a nibble. One bit here, one is one bit, 0 is another bit. So 4 bits is called a nibble, and 8 bits is called a byte, and 2 bytes is called a word. Now what is the order of a byte? Byte order or endianness. Generally machines take two types of byte orders. One is big endian format and another one is little endian format. Generally big endian machine stores the most significant byte first. For example, in this example 34 is one byte and 56 is another byte, and if it is in big endian format, 34 is the most significant byte, so we have kept it first, and 56 is the least significant byte, so we have kept it at the end. So this is big endian format. The same thing in little endian format is the least byte will be kept first, and the most significant byte will be kept at the last. So this is little endian format. This is a representation of bytes. And similarly we have another example where we have taken 56, 34. We have just reversed the previous example. So in this case little endian format will become 0x34 56, and big endian format will become 0x 56 and 34. And in our examples we are using Intel X86 architecture, so we use little endian format throughout the examples. So let us try to understand the basics of computer architecture. We have started with 8086 processors in 1978. It's X86 architecture, the computer architecture, and was called X86 to show that they all ended in the number 86. And we used to have 32-bit processors, and those are called X86 32. This is the representation for 32-bit processors. and for 64-bit processors this is the representation cross 86 and 64. And the basic difference between 32-bit and 64-bit processor is the register. Before understanding the difference between these two, we need to understand what is a register. A register is a small amount of storage used by the CPU, where the CPU keeps the data it needs to access the quickest in order for optimum computer performance. Now let us understand the bits. The bit designation refers to the width of the register. It means if it is a 32-bit register, it holds more than a 16-bit register and an 8-bit register. Similarly, if it is a 64-bit register, it can hold more data than a 32-bit register. So this is the width of the register. The bits 32 and 64 entitles the width of the register. So the more ample the space in the CPU's register system, the more it can handle, especially in terms of utilizing the system memory. Now a CPU with 32-bit register can have a ceiling of 2 power 32 addresses within the register. This is equivalent to 4 gigabytes. Hence it cannot support more than 4 GB of RAM. Whereas in the case of 64-bit registers, it can have 2 power 64 addresses within the registers, which is very huge. Now let us try to understand the CPU registers. We have in 32-bit architecture 1, 2, 3, 4, 5, 6, 7, 8 registers, and another one is EIP that we haven't included here, which is instruction pointer. Now EAX is the accumulator register, which is used to store the results of our calculations, and this EBX register is not designed for anything specific, but it is completely free for extra storage space. And ECX is the count register. This is a universal loop counter. It functions similar to a variable we use to set up loop counter value. And this EDX is an extension to the accumulator, and it is useful for storing data related to the accumulator's current location. And then we have EBP. EBP stores parameters or variables on the stack. The base pointer holds the location of the current stack frame. We'll see what it is. The full form of EBP is extended base pointer. I forgot to tell. EAX stands for extended accumulator register, and EBX stands for extended base register, and ECX for counter register, EDX for data register, EBP for extended base pointer. Now ESI, it holds the location of the input data stream. Whatever the input we are taking, the registers are taking, the processor is taking, it holds the location of that input data stream. Now EDI points to the location where the result of a data operation is stored. In other words, every loop must store its results somewhere, and this destination index points to that place. And finally we have ESP. It is the stack pointer. It always points to the top of the stack. We will see a couple of other registers among these registers in couple of other slides. We will try to have a deeper understanding of what these registers do. And now when a register is referred to by its extended name, it means, you can see here we have removed E in this EAX. So we are in this 32-bit architecture, 32-bit register, we are using E as an extra one. So when a register is referred to by its extended name, it indicates that all the 32 bits of the register are being addressed, and these registers can be broken into similar subsets of themselves, and the first 16 bits of each register can be referenced by simply removing the E from the name. You can see here, this is the AH, which is broken, AX has been broken into AH and AL. Now additionally, registers, we can just remove this E from this EAX, and we can represent it as AX for the first 16 bits. Now this AX in turn can be broken into AH and AL. 0 to 7 AL and 8 to 15 AH. This AL stands for lower addresses and AH stands for higher addresses. Similarly, the other registers also can be broken into the further subsets of themselves. And now let us try to understand the parts of the memory. We have three parts in the memory. One is code segment, and another one is data segment, and another one is stack segment. This code segment contains instructions that the processor executes. It means the actual program instructions that are being executed by the processor. And the data segments consist of variables and the dynamic buffers. And finally, the stack segment consists of it is actually used for passing the data to the functions. It is very useful. This stack segment is very useful when functions are getting called. We'll see an example of how it works, this stack segment. But to understand the stack is a piece of the process memory. It's a data structure that works LIFO, last in first out. We'll see what it is. And a stack gets allocated by the operating system for each thread, and the stack is pretty fast but limited in size. Whenever a function is called, a limited amount of size will be allocated for a stack by the operating system. Now if you go further to understand the stack, there are two operations which are very, very important on a stack. One is push and another one is pop. Whenever we try to push, an element will be added to the top of the stack. Now we have no elements in the stack, and this will be the top location of the stack. So if we try to push some element onto the stack, the element will be pushed into this location, and this is how it happens. Now we have this location as the top of the stack. So if we try to push some other element onto the stack, element will be pushed onto this location. So similarly, we can push one more element onto the top of the stack. So every time we try to push an element, it will be pushed onto the top of the stack. Simply, in other words, pushing is adding elements to your stack onto the top of the location. Now we have one more operation, that is pop. Pop will remove one item from the top of the stack and it puts in a register. It means if we try to pop the element from the top of the stack, it will be removed like this, and if we try to pop one more element, it will be popped out from the top of the stack like this. So this is how pop operation works. Now let us try to understand what is stack pointer. Stack pointer will always point to the top of the stack. It means if we try to delete one element from the stack, currently the stack pointer is pointing to the top of the stack, which is the top element. Now if you delete this, if you pop this particular top element like this, now the stack pointer will be pointing to the top of the element. This is how a stack pointer works. And now let us try to understand the stack further. Whenever a function is entered, it means, let us say function A is calling function B. Now we have entered into a function. Now a stack frame is created. This is just some information on the stack, and that is filled in and organized. When function A calls function B, a stack frame is pushed onto the stack. A stack frame consists of stack frame pointer, which is SFP, and return address. This is the location of the next instruction in function A. Because function A has made a call to function B, after completing the execution of this function B, it has to go back to function A. It has to execute the next instruction, and address of that next instruction will be stored in this return address. Now SFP holds, the stack frame pointer holds the location of function A's SFP. It means the function A's stack frame pointer, and the location of the current stack frame pointer will be stored in a register called EBP, extended base pointer. So to be clear, when function A calls function B, it first pushes the address of the instruction after this function call. This becomes function B's return address. Now function A pushes the location of its own saved frame pointer. Now stack frame is almost complete, and then it jumps to function B. Now whatever the code is there in function B, it will be executed. When it is done, it will go back to function A, and this is what a stack frame pointer is. Now let us try to understand some basic assembly instructions which are very useful. The first one is push EAX. This will push the EAX value onto the stack, its accumulators value. Now pop EAX, it will pop the value of EAX from the stack to a register. Now call some address. This particular instruction will make a call to a function at this particular location, which is 0xaddr. It's the address. Now move EAX10. This particular instruction will move this value 10 into accumulator register. Add EAX. What this does is, it will add the value 10 to the value of EAX register, and it will save it in EAX. Now the next instruction is jump some specific address. What it does is, it will jump the flow to a specific address. And the next one is JNE, jump if not equal. It will try to compare some results, and if they are not equal, then it will try to jump to some specific instruction. Similarly, if the comparison is equal, it will try to jump to a specific instruction. And these instructions are just to give a brief understanding of how assembly instructions work, but it will not give the complete understanding of assembly language. So you have to try to understand assembly language by following some resources on internet or somewhere else. So I'm just moving on to the next slide. Let us try to understand what are the types of exploits we have now. Now the first one is stack based exploits. When data more than the stack space has been filled out, then that type of exploits are called stack based exploits. To be more clear, it exploits the stack based buffer overflow. When data more than the stack space has been filled out, this kind of attacks occur. Attackers may manage to push some malicious code onto the stack, which may redirect the flow of the program and execute the malicious program which the attacker wants to execute. We'll try to see an example of this particular stack based buffer overflow later in this video. And the next one is heap based exploits. Heap stores the data which is dynamically created with the functions such as malloc and all. If any application takes an input from user and copies it in the memory without checking it, a heap overflow may occur. it can cause a serious damage, resulting in compromising the entire application and the system itself. It's a system as well. And the next one is format string exploits. This can be used to crash a software or to execute a malicious code. When the user input is filtered as a format string parameter, this attack may occur. Functions in C such as printf uses format tokens such as %s, %x to print data from the stack or possibly other locations in memory. For example, printf. This kind of format string parameters may cause format string exploitations. And the next one is integer bug exploits. Integer bugs are exploited by passing an oversized integer to an integer variable. It may cause overwriting of valid program control data, resulting in execution of malicious codes. And this is very brief about the types of exploits. We have lot more. We have to go and we have to explore them. And now let us try to understand the attack methodologies. The one is remote exploit and another one is local exploit. Remote exploits can be executed on the remote system. These tend to exploit the services running on the remote system to gain access to that system. For example, an FTP server taking malicious input from a client machine, resulting into a buffer overflow attack. These are called remote exploits. And now let us try to understand local exploit. This can be executed on the local machine where the vulnerability has been found and cannot be mutated to a remote exploit. Privilege escalation attacks are often done because of these local exploits. Now let us try to understand the steps in writing a simple exploit. First, we need to identify a vulnerability in the application, and we have to attach it with a debugger and try to see if you are able to override the return value or not. It means the EIP, instruction pointer, by giving some input to the vulnerable application. And step 3 is, if step 2 is yes, then try to automate the process by using any scripting language like Perl or Python. And then the last step is we have to try to inject some shellcode and redirect the execution flow. And now let us try to understand these steps in a practical way. So let us try to write a simple exploit which exploits a buffer overflow vulnerability. And now in this example, I am just going to take a very simple program. Let us see the source code of the program. It's a very simple C program. We are taking hash include stdio.h, conio.h and string.h. After then, it will move on to the main function. And let us see what it is doing. The main function is taking some arguments from the command line, and it is assigning the value 0 to a, and immediately it is printing some statement. You are in loudtest.exe. Now this is a very good example. This is a very good example program if you really want to propose a girl using your technology hacking. So the next function is overflow off, and it is actually calling the function overflow off with the argument argv of 1. Now it will go to the overflow of function definition. Let us see what happens. And this is what is being happened. It is taking the argument and it is putting into the buffer, which actually accepting 10 characters. Now after then it is copying into a variable buffer, and after then it is returning 0. And this is the vulnerable code which is having no bound checking. And then it will go back to the main function and it is checking if a equals to 1. And if you observe, a is already assigned with the value 0 and it will become 1. So it will never go into this particular if block, and this proposal of function will never be executed. And let us try to understand what happens if this proposal of function executes. Awesome, it is printing I love you, but unfortunately this proposal of function will never get executed, and it's our job to make it execute, and that is what we are going to do in this particular demonstration. And if it doesn't work, if a equals to 1 doesn't happen, it will print you hate me. It means your proposal will fail. So let us try to give this code to dev C++ application. I'm just copying it, or else close this. I'm just deleting this function, exe file I have already created. Now let me open this with dev C++ and the same function. Let us try to compile it. Compile, close it. If you try to observe the same location, a new file love.exe has been created. Now let us try to execute using a command line. Just go to this path, copy this and paste it. Alright, now we are in the current location, and now let us try to give some data. It is actually taking 10 characters, and if we give more than 10 characters, the application will be crashed. Let us try to understand what it is. A, B, C, D, E, F, G, H, which is less than 10, so it is printing you hate me, and that is obviously right result. Now let us try to give some random input which is more than 10. I am just going to give some 20 to 30 characters. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And now A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. We have given 52 characters, which is more than 10. Now if we press enter, awesome, the application got crashed. Now let us try to understand what's happening by just click here. Great, it is showing offset 66, 64, 64 and 63, and this is the value of EIP, the next instruction to be executed. We are actually filling the buffer and we are redirecting it to this particular address, and this 63, 64, 65, 66 is, I'm just copying it and pasting it in the notepad. Let me close this application first. This 63 is, I don't know what it is, so let me just, it is in some format which I cannot understand, so let me go to Google and try to understand what it is. It is hex format of the ASCII value 99, and which in turn represents small c. So this is the value of small c which we have actually entered into that application. So this is C and D, and this is E, and this is F. So we have 4 characters. This is the address of your EIP, but as we discussed, we are using Little Endian format, so it should be like 0x 6364 6566. Now this is gonna be our address, which is C, D, E, F. So characters till A, B, C, D, E, F to A, B are accepted properly, but when it comes to C, D, E, F, the buffer is getting overflown and it is, the application is getting crashed. So this is what we want. Now we are able to find out that application is getting crashed by actually loading some EIP, some random EIP value into the EIP register. Now the application doesn't know what to execute, so that's why it is getting crashed. Now what we try to do is, we'll try to give the address of this particular proposal of function, so that instead of getting crashed, even it gets crashed, it will execute this particular proposal of function. That is the idea behind this particular attack. So the buffer is getting overflown, it is vulnerable, it is taking some external EIP value. So instead of giving some random EIP value, we will give some meaningful EIP value. So that is what we are gonna do now, but we don't know what is the address of this proposal of function. So let us try to open OllyDbg. I am just searching for OllyDbg in my system. And I got my OllyDbg here. I am just opening this. Now let me open my love.exe, which is in my folder. So I am just opening it, and you can see, if you go down, yes, we got some beautiful message. You are in love.test.exe now, and another one is you hate me, but we are interested in I love you. And if you observe, these are the opcodes, these are the virtual addresses that are being used by this program, and these are the assembly instructions that are being converted from the opcodes for human understandable format. And these are the comments we have, and these are the registers we have seen in our presentation, and this is the dump of the opcodes which we can analyze. Now we are interested in this particular I love you message because we want to display it by executing the program. Now let us try to understand where we are actually getting a call to this, from where we are actually getting a call to this function. If you observe, I'm just taking this function down. Let me minimize the window. Oops. All right. Now if you observe, we are getting a call to this function from 00401316. So let me just copy this address, 00401316, 00401316. Now let us try to exploit the function by giving this evil EIP value to our exploit function, and I am going to write a simple exploit in Perl language and see how it does. This is a simple Perl script, and in this I am taking a very simple variable which is actually taking 28 bytes of junk data, and this 41 represents capital A because this application is accepting 28 junk characters. So I'm just going to give capital A's of number 28, and then I'm going to give this evil EIP value which I have taken from my OllyDbg. This is the address of proposal of function. And now let us try to understand how we placed this address here. We have already noticed the address from OllyDbg over here, which is the function proposal of address. Now since it is in Beginian format, we have to convert it into Lillian format by changing it to 161340 and 00. Now that's what we have placed here. And now we are taking one more variable and we are assigning the value of junk data by appending this EIP value to that. Now we are actually merging them into one evil string and we are giving it to the variable exploit. Now we are printing sending exploit, we'll see it, and then finally we are calling love.exe file by giving this exploit variable as an argument. And finally we have print done. So let us try to execute this exploit Perl script and let us try to understand the output and see what happens. I'm just minimizing it. I'm just gonna open my command prompt and cd space paste the path, enter, and now execute the function exploit.pl. Awesome, the output is, this is because we have taken the EIP value of this particular proposal of function and we have given it to exploit.pl file, which is a Perl exploit, and this particular exploit.pl file is executing this love.exe file with the EIP value of this proposal of function, and in turn it is showing the output I love you, which it should not show. And this is how we write exploits to exploit the vulnerabilities in softwares, and this is a very classic example of how buffer overflow attack works.